All right, in this video we're going to continue exploring the homework assignment, the derivative and the tangent line problem. And the last video we talked about how to do homework problems 1 through 6, and here we're going to continue and talk about problems number 7 to 14. And I'm going to break it down into problems 7 through 10, and then number 11 and 12, and then finally number 13 and 14. I will cover these. I may not get to this in this video. Okay, problem 7 to 10 actually builds off of your work on problems 3 to 6. So you're going to be using your answers from 3 to 6 to continue to the work on 7 to 10. And what they're asking you to do is to find the tangent line equation. So we need to remember this critical go-to general formula that I'm going to be using often in class, which is the function can be approximated by the tangent line, which is f of the center plus f prime of the center times x minus the center. And for those who watched the last video, example 3 that I gave you, which is similar to homework problem number 3, here's the function, here's the derivative, and here's the center. So given this setup from the last video, number 7 is similar to this problem. So I found that, or I was told f of x equals x squared plus 3. I found f prime of x to be 2x, and I centered it at the point 1, 4. Okay, I guess that was given information. So as we fill out all this information, we should be able to answer the question quite simply. So f of the center is 4. They give it to us, but if we wanted to actually show the work, it's 1 squared plus 3 equals 4. F prime of the center is 2 times 1, which is 2. And right now we have 2 of the numbers plus this gives us the 3 key features for this equation. So we can create our tangent line equation for this problem. F of x can be approximated by the tangent line, which is f of the center plus f prime of the center times x minus the center. Okay. So that is the solution to the problem that is similar to number 7. Now you'll get slightly different answers because I did a slightly different equation, but this is like number 3. Okay, we'll do one more using my information from, we'll say we're doing the one that's similar to number 8. And then for my equations, I found that in the last video we are given this information, and in the last video we discovered that f prime of x is 3x squared minus 2. So from that we take off and start doing the problem, which is to identify f of the center. F of the center is 0. F prime of the center is 1. And then we can create our equation, our tangent line equation. The function is approximated by a tangent line, which is f of the center plus f prime of the center times x minus the center. Okay? And I'll draw the arrows so you can again see where those numbers come from. So visually, what I'm saying with this problem, so you can continue to picture this as an image, I have this funky looking cubic function, and out here at 1 we have a tangent line, a line that is just barely touching the curve at a singular point and has the same slope as the curve at that point. This equation here is the equation of that line. So f of x is the equation that defines the shape of the curve, and L of x is the equation that defines the shape of that dotted line. And close to the center, my dotted line is actually a decent predictor of the value of the function. Right? If I ask you what is f of 1.3, that would be pretty hard to calculate in your head. But if I ask you what is L of 1.3, that's actually pretty easy to calculate in your head. 1.3 subtract 1 times 1, you have an answer. Okay? The further away from the center you go, the less accurate the line predicts in general. Okay, that's problem 7 through 10. All right, in this example, we're going to be looking at a problem that's similar to number 11 and 12 in the homework. And what they are doing is they're giving you the graph of a function and asking you to sketch what does the graph of the derivative look like. So sketch f prime of x. Okay? And this relationship between the function and its derivative is going to be what we spend a decent amount of time exploring graphically in a later unit. But this is setting up an understanding of what the meaning of the derivative is. The derivative is the function that models slope. So if I were to look at this function, I could see that the slope of this curve is changing. Let's focus on just this portion of the graph right here. What is the slope of the green line at any point along this location? Well, any point along this interval, the slope is 0, which means the derivative will evaluate to 0 anywhere along that interval. Then from here to here, if we look at just that portion of the graph, the slope there is -1. So my function's derivative will jump to having a -1 value, because this represents the value of the slope. And then we have this transition where we're going from -1 to maybe -1/2 to maybe -1/4, all the way to this point where it's like -0. -0, that's a weird statement, to this point where the value is 0. So we increase from -1 up to a value of 0, slowly changing. So maybe what the derivative does is it's approaching a value of 0. Okay? So it goes from a slope of -1 to a slope of -1/2 to a slope of -1/4 to a slope of 0. And I'm going to actually call those out so that you can see what I mean. -1/2 is at this location, because we're not talking about the slope of the red line. The y value of the red line represents the slope of the green line. And then our slope continues to increase from 0 to 1/2 to 1 to 2 to 5, and our slope keeps increasing, and maybe it increases in a linear fashion. We don't really know because we don't have enough information to provided to us. But in general, the value of that slope gets bigger, so the y-coordinate of that red line gets bigger as well. Okay, so this is a representation of the slope of this curve. It should be noted that if I were to do this again more rapidly, there's some tricks that you can use to really generally look at this problem more efficiently than point by point. Anytime we attain a maximum or a minimum, I don't want to say anytime, but when we attain a maximum that is a shape like this, our slope will be 0, because if you can imagine, a tangent line has a 0 slope there. Likewise, a minimum has a slope of 0. Okay? In between here and here, we have negative slopes, starting at 0, slope becoming more negative, and then becoming less negative and attaining a value of 0 again. So that's what's going on with the derivative. And then from here to here, we have positive slope, and the value of the steepness of this curve is getting bigger, so probably the positiveness of that derivative also becomes a larger value. Likewise, on this portion, the graph is increasing, so all of my slopes are going to be positive. And we get something that looks kind of like that. The value is positive high, which means that this is increasing steep, and then the value is positive low, which means this is increasing but not as steep. Okay? Now that's a lot of information packed into that question, but there's this really cool thing that we've noticed here. This function is a cubic, and this function is a quadratic. Let's call this f prime. And that should match what we found out earlier, which is quite true. If we had a cubic function, let's slide this down, the derivative of the cubic function is a quadratic. That's a nice thing to notice. Okay, and I think I'm going to leave problems number 13 and 14 for you as a challenge. I don't want to walk you through how to do those. It's kind of trying to interpret the words and then draw a sketch based off the words. So I'll leave that to you. There is a variety of possible answers. I'm excited to see what people come up with. Thanks for watching. Have a good day.